Okay, we're just going to have a little review over this chapter of alpha carbon chemistry. So we've covered several different reactions. The key for all these reactions is to understand that we're using the alpha carbon as our nucleophile. And we can actually make a lot of different types of new molecules from them. So we want to look for some patterns of functional groups that help us identify which reaction was used. So if you see a molecule that happens to have this 1,3 arrangement, where you have a carbonyl and on the alpha or beta position, you have a hydroxy group. So beta hydroxycarbonyl or a 1,3 dioxo compound, it may have come through a aldol reaction. The key for this is that you have one carbonyl and one alcohol. I'm going to skip to the bottom box down there because I can also get a different type of 1,3 dicarbonyl compound or 1,3 dioxo compound. It's a 1,3 dicarbonyl or beta keto carbonyls, and these come from a Claisen reaction. Let's look at the middle box first, though. Don't forget that in the aldol reaction, if we add a little bit of heat to it, or it forms an extended conjugated system, we tend to get an alpha-beta unsaturated carbonyl. And bonus points here if you can identify why these would be useful. What would we use a alpha-beta unsaturated carbonyl for? It was a specific type of reaction that we talked about. And hopefully everyone's screaming at the screen saying the Michael reaction, the Michael reaction. So we can actually make alpha-beta unsaturated carbonyls that we can then use in Michael reactions. So the bottom box, as I mentioned, gives us a 1,3 dicarbonyl compound. Notice that we end up with a very activated carbonyl here. In fact, if you look close at this molecule that I'm highlighting in the box, there's a specific name for that molecule. In fact, there's a specific type of synthesis that uses that molecule. And again, you're screaming, McKay, of course, we know that's the acetoacetic ester synthesis. We can actually do reactions where we actually go and make essentially a alpha substituted acetone. So if you think about it, you can take ethyl acetate, fingernail polish remover, throw in a little sodium ethoxide in there. You just need to work up the product with a little bit of acid, and all of a sudden you have acetoacetic ester. And from the acetoacetic ester, you can then use it to do the acetoacetic ester synthesis. Or you can actually use this molecule here as a very good Michael donor. So if you remember, we'd like to use good Michael donors, which tend to be those that are extra resonance stabilized, doubly resonance stabilized, and those tend to be good Michael donors where we deprotonate and those attack at the beta position of the alpha-beta unsaturated carbonyl. So it's really kind of interesting. We can actually make the reagents that we use for a lot of other reactions. So just to stress that again, we can make alpha-beta unsaturated carbonyls that we use in Michael reactions. Those are made through an aldol condensation. We can actually make these very good Michael donors that are used in the Michael reaction. We can make those through the Claisen condensation. And specifically, we can actually make the acetoacetic ester just by the condensation of ethyl acetate. And then we can do all those reactions we talked about with the acetoacetic ester, including the alkylation, and don't forget that we can follow that up with the decarboxylation. So, as I mentioned, we can do Michael reactions. Now notice the arrangement of the carbonyls here. So instead of 1,3 dioxo compounds, we actually can get 1,5 dioxo, specifically 1,5-dicarbonyl compounds, and that comes from the Michael reaction. And remember that the Michael reaction works best with a doubly resonance stabilized Michael donor, but we can get around that limitation by using the Stork enamine synthesis to generate an enamine that is actually a milder way to do a Michael reaction. But again, we get a 1,5-dioxo-dicarbonyl compound from this. And lo and behold, from this compound here that we got from a Michael reaction, where did we get this from? Think about it, we got that from an aldol condensation. We made this from a Michael reaction. And if you remember what we can do with the products of a Michael reaction, we can then follow that up with an aldol, intramolecular aldol condensation, which is called the Robinson annulation. So when you're doing synthesis, you want to look for these patterns. So if you had a question that asked you to make this product here to the right, you look at that and hopefully you'd be able to identify that that is just an alpha substituted acetic acid or ethanoic acid. And that would occur through the malonic ester synthesis. If you look at the bottom here to the right, we have an alpha substituted acetone. And that alpha substituted acetone comes from the cetoacetic ester synthesis. Both of those using the dialkylation route. So we've learned a couple ways to alkylate in this chapter. One we didn't spend a lot of time on, so this is a good review. But we can actually alkylate using the Gilman reagent at the beta position. Remember the Gilman reagent, which is this species right here, actually does a Michael addition at the beta position of an alpha beta unsaturated carbonyl. And so we can use it to add one alkyl group. But if you notice, the product here also has an alkyl group at the alpha position. So we spent some time talking about how we can alkylate at the alpha position, and that required an enolate. So Klein has this very slick method to actually do a alkylation at the beta position and an alkylation at the alpha position in what we refer to as 2 steps but 1 pot, meaning you're just doing this in a single reaction vessel. You do step 1, wait, and then you do step 2. So let's see if we can come up with a reasonable mechanism for this reaction. So if we start with the cyclohexanone and we take step 1, the Gilman reagent. Remember, for our purposes, we're just going to treat this Gilman reagent as if it were a C-. So let me correct that, too many carbons. There we go. A C- for my effort in drawing the correct number of carbons. So there we go, 2 carbons. We're going to treat it as a C-. That C- is going to come in and attack at the beta position. We need somewhere for those 2 electrons to go. They'll move up to this position, which forces the electrons out onto the oxygen there. So after step 1, we end up with the ethyl group attached to the beta position, and we're left with an enolate. Well, notice, after step 1, that's all we have is the Gilman reagent. So what's sitting in solution after we add the diethyl cupric reagent is this enolate. And this enolate is just waiting for either a proton source or some other electrophile. And so in step 2, we actually add the methyl halide. And to finish up the mechanism, this enolate will collapse down, kick the electrons out. And this is perfect for an SN2 reaction. And lo and behold, we have the expected product, which is substitution at the beta position with an ethyl group and substitution at the alpha position with a methyl group. And all based on Michael and enolate chemistry. So when we start looking, we can actually make fairly complicated molecules. So here is a question about how we would accomplish this transformation for this interesting bicyclic molecule listed in the bottom box. And so some of the termination that, or the terms that we use in organic synthesis, we talk about the disconnection. Where are we going to disconnect? So you can see that pink squiggly line. That's the bond that we need to form. So when we're doing retrosynthesis, we say, well, that's the bond that I need to disconnect. But really in the synthesis, as we go forward, that's the bond that we make. This term synthons, I mentioned it before, but it is synthetic equivalents. They're not real molecules. They're just getting an idea of where would the nucleophile be and where would the electrophile be. And once we have our synthons, then we actually have, well, what are the synthetic equivalents? What are the real reagents that would provide that synthon? So let me just show you what we mean by synthons and synthetic equivalents. So when we design this synthesis here, remember, we're trying to connect these two carbons there. And if you notice, and hopefully you're getting really good at identifying alpha carbons. So if you see a carbonyl, you look immediately to the left or right and you find that alpha carbon. And that alpha carbon can always end up as a nucleophile because we can form enolates. So the structure on the left is what we would refer to as the synthon that we need to actually make this synthesis work. If we look at the structure to the right with the big not happening sign over it, you can see that we have a negative on this carbonyl. And carbonyls are always considered electrophiles. They're always considered partial positive. And so this type of synthon that we're looking at here isn't really a good way of thinking how to accomplish this synthesis, because the polarity of the bonds is actually incorrect. Now, I'll just let you know, if we have some advanced organic chemists watching, there is a way to reverse the polarity. It's actually a fun organic term referred to as Oompa-Long chemistry, where you can actually do the reversal of the chemistry. In fact, you can actually make this synthon right here using thioacetals. For those of you just suffering through my regular lectures, you don't have anything to worry about. But now that these are posted on YouTube and I'm going famous and going to eventually become a YouTuber and leave this teaching behind, I just want everyone to know that I do know about Oompa-Long chemistry and that you can make a synthon out of this. But enough of that. What we want to do is focus on this synthon. And so the question is, how do I make this position into a negative, and how do I make that position into a partial positive? Well, we already know that that's a partial positive, but if we go back to the product that we want to make, I want that carbonyl here. So if I'm going to use this carbon right here as my nucleophile, the question is, how do I retain that carbonyl? So I end up with a 1,2,3 dicarbonyl compound. And the question is, well, how do I get a 1,3 dicarbonyl compound, especially a cyclic one? Now, this is what's referred to as a Claisen-like condensation. Since it's a intramolecular one, it's more like a Deichmann cyclization, except we're not doing it between two esters. And I'm not quite sure. I think this is kind of a modification of a Claisen-Schmidt type reaction, where you actually have one enolate from a ketone attacking an ester. Either way, it's like a Deichmann or like a Claisen, where we're forming a ring and we retain the carbonyl, which means that at this position right here, I actually need a leaving group. So to do this synthesis with the molecule that we start with, which is given here, they gave us this molecule, I need to be able to make that into a nucleophile. And you notice what they gave us is a carboxylic acid, which is a very poor leaving group. So I need to convert that into a good leaving group. And the leaving groups that we've seen that work really well with alpha carbon chemistry are esters. So I can quickly turn that carboxylic acid there by SOCl2, making that OH into a Cl group. And then I can do a nucleophilic acyl substitution reaction. I can convert that acid chloride into the ester. And so now I have a good leaving group right there, which is what I need in order to retain the carbonyl in my product. And then finally, I just need to do this cyclization, this Claisen-like reaction. So I need to deprotonate at that position. Since I'm attacking an ester, a good way to do that would be to pick a base that matches the ester there. And since I have a methyl ester, I'm going to use methoxide as my base. And so what I do is I have the base deprotonate that position there. It generates the carbanion, which can then come in and attack that carbonyl, electrons up, down, and kick out the leaving group. And you get your 10 points. And maybe even a smiley face. Okay, so there's some thinking in how to design a synthesis. I can't stress it enough that if the question says, hey, make this, and we give you this, spend time comparing those two and identifying what you need to do to accomplish that transformation. In this one here, I need to make bonds between that alpha carbon right there and these alkyl groups. Specifically those carbons. Let me highlight those carbons again. Let me permanently highlight those carbons. I need to make a bond between those orange carbons and that green carbon. Well, that green carbon is an alpha carbon, so I could use that as a nucleophile. And then the question is, well, what am I going to have here, these orange carbons? Well, if we take this idea of synthons and retrosynthesis, I need to make those carbons partial negative because this guy right here is going to be partial negative or even a full-blown negative. It's my enolate. So we look down here at this example. This is how we would think about the synthesis. I need 2 negatives there. Of course, I'm never going to be able to generate 2 negatives at one time. This is just the mental exercise that we go through. So that would take a negative and go to that positive. That would take a negative and go into that positive, and that would make my molecule. But in reality, how do we do that? Well, I can actually take this molecule right here and say, oh, well, I'm never going to get 2 full-blown positives, but I surely could get some partial positives on those carbons if I had a halogen attached. And you're almost done. So then what we do is take the molecule that we started with. They gave us that. We take a base and deprotonate at the alpha position. So I pull that H off, park the electrons there. That would give me this enolate. It looks like a sad enolate, but that enolate would come in, attack that position, and kick off the bromide, which would give me this product here. So we've alkylated once. Remember, if we're going to alkylate twice, we have to do this step twice. I'm going to deprotonate again. Let's see if I can make a happier enolate. Oh, there we go. Oh, he disappeared. Okay, happier enolate that comes in, does an SN2 reaction. And we now have this cyclo group. Those of you playing along at home, let's see if you can figure out what would be the product of this reaction here if I took H3O plus and some heat. Dun, 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 dun. Okay, what's your answer? hopefully your answer would be cyclohexane carboxylic acid. Woohoo! Yay! Plus 10 points. Okay. So we've got another design, a synthesis. So in this question here, what we've got is a 5-membered ring. We've got this alkyl group out here. And what we're trying to do is construct it. They've given us a starting material right here. Notice it's a diester. So it's actually we're going to be able to do a Claisen-like reaction with it. And so I need to make a ring. So what we want to do is make a ring and find some way to also put this alkyl group on there. So this is a little bit more of a challenging one. They give us kind of a hint over here of what we need to do. I need to get a ring. So let's tackle that first. So if I take this alpha carbon here and I attack this carbonyl, I need to end up with a 5-membered ring. So let's see if that's possible. If I pick this alpha carbon here and count 1, 2, 3, 4, 5, oh, perfect. I can use that molecule to make a 5-membered ring. And this is just a perfect setup for a Deichmann reaction. So we're going to take the base, deprotonate. That gives us this enolate here. And that attacks the carbonyl up, down, and it kicks off the leaving group. So we don't want to stop here. That gets us a 5-membered ring, but we need to include our alkyl group. I need some way to add an ethyl group right there. And so to this carbon, I need to add an ethyl. So if we look, that's actually a doubly resonance stabilized position. And so I can just deprotonate it, which is easy enough to do. I'm going to use a base, again, that matches the ester, and deprotonate it. And then just simply do an SN2 reaction with that enolate on ethyl bromide. But now we're left with too many carbons. This group right here, we don't want it in our final product. And so we need to get rid of it somehow. So a little bit tricky, but hopefully you're starting to recognize that I can get rid of those groups. And I've just realized that everything I've drawn on my screen has not shown up here. So let me pause for a second and fix that, and I will be back. Okay, I think I got it fixed. Sorry about that. Instead of repeating everything I just said, I'll quickly run through it. We want to make this 5-membered ring here. We need to add this alkyl group in orange. And we're going to use this position here. We want to maintain that carbonyl. And so I want the leaving group. So when I was talking earlier, we've got an alpha carbon here, and we're going to count 3, 4, 5. And that's perfect for a Claisen reaction. So I can just take this position, deprotonate it, kick those electrons up, down, and a leaving group will leave. Notice the base that we use, again, matches the type of ester that we have. And we end up with this product right here. So if we look at that product, it's not the same as our desired product. Okay? So you don't want to stop here. You realize that alkyl group in orange, I need to add to that orange spot right there. So again, we use a base that matches the ester on here, deprotonate, and then simply do an SN2 on the ethyl bromide. And that gets us to this final spot, well, next to final, penultimate spot right here. And I need to get rid of that green group. Now that green group is an ester, but if I heat it up, or sorry, if I add a little bit of acid in there, I can actually hydrolyze that ester. And that may give you a hint of what we're doing here. So if I hydrolyze that ester, I get this carboxylic acid there. I just got rid of the ethanol off of there. So in black, we now have that carboxylic acid. And that carboxylic acid, what we have is the alpha position beta keto acid. And that's something that you should be able to recognize. Beta keto esters can be converted into beta keto acids. And these beta keto or beta carbonyl acids, with a little bit of heat, undergo the decarboxylation reaction. So we saw that in the acetoacetic ester synthesis. You also see that in the malonic ester synthesis. But as I mentioned, you can actually see it in many different reactions. All you need is a carbonyl and a beta carboxylic acid. So in fact, in Deichmann condensations, you're always going to end up with the possibility, because this is just a Deichmann condensation right here, where you could actually decarboxylate this thing. If you decided to just add HCl and some heat at this point, you would actually just end up with cyclopentanone. So from Deichmann condensations, that you always have the option to decarboxylate and end up with just a single ketone. In fact, that's probably true for even Claisen reactions as well. You always have the possibility to do a decarboxylation. Oh, sorry, someone's trying to call me. Okay, it's my wife, so I better hurry up. So what we can see is if we do the decarboxylation here, add some heat, then we can actually get the alkyl group there. So we're almost done. Just remember all the types of reactions that we've seen here. We can do the alpha halogenation of carbonyls. We can do it under acidic conditions. Key point there is under acidic conditions, we add once. We can actually do halogenation under basic conditions, and basic conditions add as many times as we have alpha carbons. And in special cases, when I have 3 alpha hydrogens, we can do under basic conditions, we can add as many halogens as we have alpha hydrogens. And in specific cases where we have 3 alpha hydrogens, specifically in a case what we refer to as a methyl ketone, you can undergo a haloform reaction. We really can't do halogenations directly on carboxylic acids, but we can play a trick. We can use a Helvol-Hart-Zielinski reaction, and we can actually end up halogenating at the alpha position to a carboxylic acid. The whole trick there is that we actually turn this into a bromine, and we actually do our reaction on an acid bromide. And then when we add water, we actually convert it back to a carboxylic acid. Oh, looks like I'm a wanted man. Just one second. Oh, it's a busy day here. So, sorry, we'll finish this up, let you guys get on to studying and prepared for your quiz. So if you have a methyl ketone, right there, you can actually undergo a haloform reaction, which actually gives you a carboxylic acid. Okay, don't forget aldol reactions. We've got the aldol addition. It gives you a beta hydroxy carbonyl, and you can do the aldol condensation. It gives you an alpha beta unsaturated carbonyl. You can do crossed aldol condensations. Again, we have some tricks there. One trick is you only have 1 molecule with an alpha hydrogen. The other trick is that you can use LDA and control the order of operations. And then finally, we can actually do it intramolecular aldol condensation and make cyclic alpha beta unsaturated carbonyl compounds. We can do the Claisen condensation. Claisen condensations give you 1,3 dicarbonyl compounds, specifically beta keto esters. You can do an intramolecular Claisen condensation, which is known by the name Deichmann cyclization. Again, you can do crossed Claisen condensations, And remember, we have some tricks for those. One of the tricks is you only have one molecule that has alpha hydrogens, as well as you use a strong base like LDA to give you 100% enolate. We can alkylate carbonyls. And if we have a carbonyl, such as the one shown here, that we actually have different substitution, we have a less substituted alpha position here, got a more substituted position here. We can actually do kinetic control, big bulky base, low temperatures, and alkylate at the less hindered site. Or we can do thermodynamic control, where we use a smaller base and like room temperatures, and you can alkylate specifically at the more substituted site. We can also alkylate these malonic esters and undergo a decarboxylation, so we end up with a alpha substituted acetic acid. And you can do the acetoacetic ester, where you do a substitution at the alpha position, do a decarboxylation at this step here, and you end up with an alpha substituted acetone. So lots of variations here. We can do Michael additions. We just need good Michael donors. Gilman ends up being one of those good Michael donors. We can alkylate at the beta position. So contrast that with the previous slide where we're alkylating at the alpha position. So we can also alkylate at the beta position, but we need an alpha beta unsaturated carbonyl. And no worries, because we can make alpha beta unsaturated carbonyls all day long by the aldol condensation. We can do the Michael reaction with good Michael donors, those that are doubly resonance stabilized, and an alpha beta unsaturated carbonyl. If we only have a single carbonyl, we can actually use the Stork enamine synthesis, much more mild conditions and some advantages. And don't forget that once we do a Michael reaction, so we can attack here, we can do an intramolecular aldol. This is known as the Robinson annulation for making rings. And so we can actually make really interesting molecules. Again, this is a 1, 2, 3, 4, 5, 1, 5 dicarbonyl compound. So that should give you a hint that that comes from a Michael reaction. This is also a alpha beta unsaturated carbonyl, and that should give you a hint that it comes from an aldol condensation. So what you want to do is make the 1,5 dicarbonyl compound first through the Michael reaction, and then follow it up to make the alpha beta unsaturated carbonyl, and that comes from the aldol condensation. Yay, we're done with this chapter. As I said, I'll get the amine chapters posted soon. And hopefully you're enjoying your time. Don't forget to take some time to have some fun. What am I saying? The fact that you're listening to me means that you're having fun. Organic chemistry is fun.